Are you going to make an introduction or anything, or should I immediately
Uh,
start?
yeah, I can make a very brief introduction. I think several people have been watching us talk. So, so welcome everybody. So the first talk of the evening session today is by Professor Erdem Ashar, right?
Yes.
Of the University of Economics and Technology TOB in Turkey. And he's going to talk about surrogate-based optimization today. So please stay on mute if you have questions. Is it okay if they ask you as we go, or do you want to wait for them to, or wait for the talk to be over to ask?
They can ask as we go. Yeah.
Okay,
Sure.
so we can ask questions as we go. You can also type your questions in the chat window, and either me or Akshay or both will be monitoring. So with that, please, you can get started.
Thank you very much for this nice introduction. My name is Erdem Acar. I am a professor at the Department of Mechanical Engineering of the TOB University of Economics and Technology, which is located in Ankara, Turkey. My talk is going to be on surrogate-based optimization. And during my talk, first I am going to define you what is a surrogate model, and then try to motivate you for using these models in optimization. First, I am going to talk about how we are constructing a surrogate model. And then I am going to mention different surrogate model types that we have. For instance, polynomial response surface, radial basis functions, kriging, support vector regression. And then I am going to introduce you a concept called ensemble of surrogate models in order to improve the robustness and accuracy. And then I am going to mention major issues that we have with surrogate-based optimization. Then I'm going to have some application problems for you so that you can imagine your research subjects, and then you can get inspired and use the surrogate models in your work. And then I'm going to conclude my talk with some remarks. First, let's define what is a surrogate model. Before this definition, let me give you a motivation. And motivation is based on this. The design of complex systems such as aircraft and automobile, they require performing high fidelity analysis like finite element analysis or CFD analysis in order to ensure the accuracy. And Venkataraman and Hafka, by the way, Hafka is my PhD advisor, they reported in 2004 that the analysis models of acceptable accuracy have required at least 6 to 8 hours of computer time, which is an overnight run, throughout the last 30 years. And now we are in 2022, and this comment is still valid, because if we have a high fidelity finite element analysis model or a high fidelity CFD model, it took 6 to 8 hours of computer time in order to have an acceptable level of accuracy. And there is a growing interest in replacing these slow and computationally expensive and mostly noisy simulations with some smooth approximate models that can produce fast results. And these mathematical models, these approximate models, are usually referred as surrogate models or meta models. And surrogate models are widely used in optimization because design optimization requires to evaluate many designs. Over here, we can see an optimization process. In optimization, we have to identify some design variables. Let's denote them with X. We have some objectives. Let's denote them with F. And we have some constraints G. Let's give some examples. For instance, if you are designing a beam, then your design variables can be the width and thickness of that beam. And we have an objective function that we want to minimize or maximize. And in our structural design, the objective function f is usually the weight. That is, we want to minimize the weight. And we have some constraints g. An example of constraint is that, for instance, maximum von Mises stress developed in the beam shouldn't exceed some allowable values like yield stress. If we consider a complex problem, then we compute these objective functions or constraint functions through computationally expensive simulations like finite element analysis or computational fluid dynamics analysis. And since optimization is iterative, we have to perform this finite element analysis again and again. So it is going to be computationally very expensive. So we seek some approximate models that can mimic the actual behavior, which are surrogate models. Then we have this approach called surrogate-based optimization approach. Over here, we replace these finite element or CFD models with some surrogate models. Here how we start, we define our optimization problem. Over here we have this optimization problem written in standard form. Then we evaluate our objective function and equality or inequality constraint functions. Then we want to construct models which relate design variables to objective or constraint functions. Then we can either go this way by identifying the most and least important variables using some global sensitivity analysis and delete the least important ones and go with the important ones. Or we don't have to go this way. We go with all the important and least important variables and perform optimization. After we perform optimization, there is a validation step. That is, the optimization found using surrogate model may not behave actually as we desire. So we have to make an additional single finite element or CFD run in order to ensure that the real performance of the optimum found is validated. If the answer is yes, then optimization process is stopped. If we cannot validate, it means that there is some errors in the surrogate model so that the optimum that we found also is erroneous. Then we can either refine our design space so that we construct our models in a smaller portion of the design space, or we can increase the number of simulations so that as the number of data points increase, then the accuracy of the surrogate models is also increased. This loop also, then we go to loop that I mentioned earlier. We perform these iterations until our validation is being done. How do we construct a surrogate model? This is the question. Surrogate model construction, it consists of 4 steps. In the first step, we generate some training or data points by using a proper design of experiment technique. And then we perform some performance analysis using either finite element analysis or CFD analysis at these data points or training points. Then using the training points constructed through a design of experiment technique and the corresponding response values or performance values, then we construct our surrogate models. Construction of surrogate model means finding the parameters of that mathematical model. Then we assess the accuracy of the constructed surrogate model by using some metrics. Over here we consider a problem where we have 2 variables, like design of this beam. You can vision that this axis is the width and this axis is the thickness. And then we select some points using a proper design of experiment technique. And then at those points, we generate our response values. And then we perform this response surface construction or surrogate model construction so that we now have a mathematical model. And then we can use this mathematical model in our optimization process. Here, I mentioned about this design of experiments. What is design of experiments? Let me talk about it. Design of experiments is a sampling plan in our design space. That is, the locations where we conduct our experiments or simulations. So the question is how many number of data points or training points that I have to generate. The rule of thumb is that if you are using a polynomial response surface model, then the number of data points should be 1.5 or 2 times the number of coefficients in the fitting polynomial. Another rule of thumb is the number of training points should be at least 10 times the number of design variables. If we have a 2 design variable problem, then we should at least generate 20 number of data points. Now, selection of this design of experiments it depends on the influence of noise, bias error, extrapolation. Over here, if the noise is too much, then I would like to use a classical design of experiment like CCD. But if the noise is small, then I can use some space filling technique like LHS. Similarly, if I want to use some extrapolation, then I may want to go with the classical design of experiment. If I am not using an extrapolation, then I can go with Latin hypercube sampling over. Trying to go to the next slide, but somehow my computer has frozen. Yeah. But if you are using a polynomial response surface, then there is one problem that can face, which is curse of dimensionality. That is, as the number of variables.
Sorry to interrupt you, Professor Ajar.
Sure.
So one of the audience is indicating that your voice is a bit on the lower side.
Okay. How about now?
This is much better. Thank you. Yeah.
Okay. Okay. One of the problems with surrogate models is the curse of dimensionality. That is, as the number of variables or the order of polynomial in the response surface increases, then the number of coefficients in our mathematical model increases. Then, if the number of coefficients increases, then the number of training points required is also increasing. So, it is not advantageous. Let me give you one example. If your number of variables is 2, let's say, and you are using a third order polynomial, then you have 10 coefficients that you want to compute, as you can see here. But if the number of variables is, say, 10, and you are using a cubic polynomial to fit, then you have 286 simulations. Then if we consider our rule of thumb, then we have to perform at least 400 simulations. Considering that one simulation takes about 6 to 8 hours, then this computational budget is not manageable. Then what we have to do is we have to limit ourselves with maybe a quadratic polynomial. So polynomial response surface has this mathematical form, and over here we want to compute these beta values. That is, construction of surrogate model in when we use polynomial response surface is the calculation of the coefficients over here, and luckily we can analytically compute these coefficients by using this simple formula. In polynomial response surface, our assumption is that we have an uncorrelated and normally distributed noise. In the presence of noise, the constructed response surface, by the way, it can be more accurate than the observed data, since if the data is obtained through, for instance, experiments, we may have experimental error, or considering a crash problem, car crash problem, then the simulations can be noisy. Now, our question to ask is that, do we have a numerical or experimental noise in our response values? If so, we want to use polynomial response surface maybe. And then another question to ask is that, can the chosen order of polynomial approximate the behavior, considering the curse of dimensionality that I mentioned earlier? Another mathematical model or surrogate model is kriging, which is more advanced than polynomial response surface. Over here, our prediction has two components. The first component over here is a trend model, which is a general trend trend of the data values with respect to the design variables. And the second term is about systematic departure. Now, this kriging is named after a South African mining engineer, D.G. Kriging. And the assumption in kriging is that these systematic departures that I mentioned are correlated and noise is small. Usually, this correlation is modeled with Gaussian correlation function, which is more popular, but we have also a linear model or exponential model that we can also use. The kriging model is computationally expensive for large problems. That is, if the number of simulations are more than 200, then construction of this kriging model, it also takes time. Another surrogate model is radial basis functions. Over here, you consider a linear sum of radially symmetric functions. Those examples of those functions are template spline, Gaussian, multiquadratic, or inverse multiquadratic models. These radial basis functions are found to be good for modeling fast-changing responses, and we have seen successful application here in prediction of crashworthiness responses. Another surrogate model is the support vector regression, SVR. And if this support vector regression is used in the linear regression mode, then we have this dot product, as we can imagine. And in construction of support vector regression, we want to make our prediction as flat as possible. It means we are solving this optimization problem over here. If we do some soft formulation, write Laplacian, write KKT condition, and substitute KKT to Lagrangian and solve the optimization problem, we have this support vector regression mathematical function. And over here, we want to replace the dot products with some kernel functions in nonlinear regression. Usually, Gaussian kernel functions are used. This support vector regression is based on the generalized portrait algorithm developed by Vapnik in Russia. See, when we want to use surrogate models in our optimization problem, then the question to ask is, what surrogate model or which surrogate model I have to use? Because there exist many surrogate models. It is difficult to know beforehand which one is going to be the best for our problem, because the performance of surrogate models depends on the number of samples that we use, the sampling scheme that we choose, or nature of the problem. So the main issue over here is that finding the best surrogate model is a problem, and also design of experiment dependent question. Now, our question to ask is that since surrogate models are inexpensive to construct, can we do better by using several surrogate models at once? That is, instead of constructing many surrogates and then choosing the best one, can we combine them and make our prediction based on this combined form? The advantages can be, it can protect ourselves by using the wrong surrogate models, and estimation accuracy can also increase. Weighted average model is a simple model to combine various predictors, that is, various surrogate models. If assume that we have an m number of surrogate models, then our ensemble or weighted average model can be written in this form. And over here, W are the weights corresponding to the ith meta model or surrogate model. As the number of accuracy, as the accuracy of a surrogate model increases, then we should have assigned higher weight to that model. inherently. The weighting strategy of Goel in 2007 is based on a parametric weighting strategy, and over there they used press error, predicted sum of squares. And in this formulation, they have this alpha value, which is selected based on experience, and they have found that 5% alpha is performing well. Now, instead of this weighting strategy, parametric weighting strategy, there is another way to determine the weights, and which is by solving through an optimization problem. That is, we want to minimize the error of our weighted average model such that the optimum values of the weight factors are being determined. If you construct a surrogate model, whether it is an individual model or an ensemble model, we have to determine if these meta models or surrogate models are accurate enough to be used for analysis and optimization. In order to assess the accuracy, there are some error metrics that we can use. Usually, it is a good idea to use test points. That is, we have to monitor the performance of our surrogate models at some test points which are independently generated from the training points. However, if our computations are expensive, such as taking 8 or 10 hours, then we may not have this luxury of generating test points. In that case, we can do cross-validation error. That is, using the data to estimate the errors, which is generally we use leave one out cross-validation error. That is, if we have, for instance, 20 training points, we select the first training point out, then construct the surrogate model using the remaining 19 simulations, and then test the accuracy of the surrogate model in the first point that we subtracted from the data. If we do this operation for each and every point, each and every training point, then we can have some prediction on the accuracy of the surrogate models. If we are using a polynomial response surface, then an R-square value, of course the adjusted value makes more sense, or the root mean square error at the data points can be used. However, if we are using a kriging model, then we cannot use these errors at the data points, because as we have seen that in kriging, for instance, the kriging prediction passes through all the training points. Also, there are some estimators like prediction variance that can be used in order to measure the accuracy of the surrogate models. Let me speak on major issues in surrogate-based optimization. See, the success of surrogate-based optimization depends on the accuracy of the surrogate models, obviously. But there are some sources of uncertainties in our surrogate model or meta-model predictions. There can be noise in the data, or accuracy of the numerical models or simulations may be insufficient, or we have chosen wrong sampling strategy. Due to those wrong selections or noises, we have some errors in our surrogate models, and it limits the optimum that we found through surrogate model use. In that case, as I mentioned in our earlier slides, the surrogate-based optimization should end with some validation checkpoint. Until here, do we have any questions from the audience? Because afterwards, I'm going to speak on application problems. Any questions?
I don't see any chat messages.
Okay. Okay.
Any?
Yeah, let me go with application problems. Maybe it is going to raise some questions. During this talk, I am going to mention three application problems. The first application problem is redesign of an aluminum cast control arm. In that problem, the baseline design was based on experience, and redesign is obtained by using surrogate-based optimization techniques, and we reduced the weight by 25%. In the second optimization problem, we have this blade disc forgery joint. Over here, we started with an infeasible design, and we performed the redesign by using optimization techniques, and I'm going to show that now the design become feasible. And I have one application problem on ensemble of surrogate models. Our first problem is size and shape optimization of aluminum cast control arm. This is an control arm of Corvette made of aluminum 356. This control arm is designed for panic brake and pothole conditions. The shape and size of this control arm can be designated by using 13 design variables that we can see over here. For instance, the first design variable is the wall thickness of this member. Second design variable shows the wall thickness of this member, and so. Our optimization problem is aims for minimum weight. That is, we want to minimize the weight of this control arm such that the maximum von Mises stress developed in this control arm doesn't exceed some critical stress. Over here, we used yield stress. Since the calculation of this maximum von Mises stress is through an expensive finite element analysis, then we used meta models or surrogate models in order to alleviate the computational burden. We have used different surrogate models like polynomial response surface, radial basis function, Gaussian process, Kriging, feed-forward neural network, or support vector regression, and we found out that Gaussian process was performing the best for this problem. And once we constructed our Gaussian process model, then we integrated that model into MATLAB's fmincon function that uses sequential quadratic programming for solving the optimization problem. We find out that the von Mises stress predicted using Gaussian process was 361, and we made our final validation run, and we found out that the actual von Mises stress was smaller than that value. So we were in the conservative side. And when we checked out normalized weight, we find out that we reduce the weight of this control arm by more than 25%. And these two slides show the baseline and the optimum design that we obtained. Second optimization problem was blade disc forgery joint. Now let me give you some introduction on this problem. The structural integrity of blade disc forgery joint has a strong effect on operational safety and service life of gas turbine engines. The stresses over here in that contact region are mainly governed by the centrifugal forces, the bending, and the torsion due to gas pressure. And also thermal loading is also important for this member. In order to define the geometry of this forgery joint, we identified 9 major geometrical parameters like shank width, contact angle, face angle, flank angle, two more contact lengths, lobe radius, groove radius, so on. And these parameters, geometrical parameters, are used as design variables in our optimization. In optimization, minimum weight was our objective function, and the yield stress of the blade material and the disc material was different. So we use sigma YB and sigma YD in order to denote the blade and disc material yield stress values. And in case of failure, we desire section 1 and 4 to fail first. Overall, there are 10 responses appeared in our optimization problem, as we can see from here. We perform a 2D stress analysis using ANSYS. The loading and boundary conditions are shown over here. Since it is a symmetric problem, we utilized that info. And this joint is meshed using quad tree method. The element sizes in the curved on contact regions are kept smaller in order to capture the stress concentration and the contact behavior. Over here, for this simple problem, we use 16,000 elements in our finite element model. And the company gave us some baseline design. And when we performed the structural analysis, we found out that the baseline design was infeasible. That is, the peak groove stresses were larger than that we wanted. Also, peak disc upper stress value was larger than we desired. And the section 1 to section 2 stress ratio was smaller than that we desired.
We have a question.
Yeah.
The question is, what is the basis of choosing the powers of the data points? I think they mean the polynomial powers.
Polynomial powers.
Order of the polynomials, yes.
Order of the polynomial. It depends on the computational budget that you have. As we see in polynomial response surface, if a quadratic polynomial is constructed, then it is okay. But if you increase the number of polynomial, increase the power of the polynomial to 3, then for even a 10 variable problem, it is problematic. Let's go to that slide that we have. Yeah, this slide is informative over here. Assume that our number of variables is 10, as in the case of this control arm problem, for instance. I think it was more than 10 in the control arm problem, maybe 13. But assume that you have 10 number of variables. If you use a second order polynomial, then you have 66 coefficients. Remember the rule of thumb. The number of data points should be 1.5 to 2 times the number of coefficients. If we apply this rule over here, we need to generate at least 100 number of data points. That is 100 number of finite element simulations. Now, if we increase the number of if we increase the power of the polynomial from 2 to 3, then the number of data points required increasing from 100 to 400. So if we have this computational budget, then we can go with third order polynomial. But usually people use second order polynomial. At most third order polynomial. Because if you go to, for instance, for this 10 variable problem, if you increase the power to 4, then number of coefficients is 1,000. So you have to perform at least 1,500 simulations. That seems too much.
Sir, will it increase the accuracy if we increase the order polynomial?
Excuse me?
Yeah, will it increase the accuracy or like correctness? Or will it decrease the, what we can say that?
Depends on the, see, if you increase the number of, if you increase the power, then you might be then you might be fitting to noise instead of the actual behavior.
Okay,
If your
yes.
simulations, if your simulations are noisy, for instance, like here, you have these noisy simulations, and maybe this is the general trend in the physical, you know, if you consider physics of the problem, maybe it is the trend, is quadratic trend that you have. But if you increase, for instance, to 10th order polynomial, then you can pass through all these data points. But then it means you are fitting to noise instead of the actual behavior.
Okay, thank you. Yeah, got it.
Okay. Yes. In this 4-3 problem, the company gave us a baseline design, and our finite element simulations declared that this baseline design was infeasible. Then what we did was we generated 180 points by using Latin hypercube sampling. And first we used 110 points for surrogate construction and these 70 points for testing. And the accuracy of surrogate models are found to be satisfactory. And then we combined these training points with these test points, and we constructed a new surrogate model and used that in our optimization. We use polynomial response surface, radial basis functions, and kriging. And we find out that polynomial response surface was the most accurate for all responses. But still, we performed the optimization using all these three types of surrogate models because in an earlier study, we found out that the use of most accurate surrogate model does not always lead to optimum for all problems. And the optimization resulted with these predictions. We have seen that peak groove stresses violation was reduced. Peak upper disk stress violation was removed. Section 1 to section 2 stress ratio is improved, but it resulted in 9% increase of mass. When we see the optimization results, we find out that for these 4 design variables, we were in the either lower limit or the upper limit. Then we selected expanding the design space, and we performed the optimization again. In the second run, we find out that except from the 1% violation in the peak groove stress, now the design become feasible with 10% increase in mass. And then we told that we may increase the improvement by adding more design variables to the problem. We revisit the problem and we find out that shank height and disk height can also be used as our new design variables. And then by addition of these 2 more design variables, it improved our optimization results. There was no constraint violation. Stresses are significantly reduced, but our mass is increased by 17%. But now, at least for this problem, we don't have any constraint violation. The design becomes safer. And as I told, we start with an infeasible design point. First, we started with 9 design variables. We have seen that stresses were reduced, even though some constraint violations remained. Then we expanded our design space, and we find out that some of the constraint violations are removed, and we only had one slight constraint violation. In order to get rid of this violation, we added 2 more design variables into the problem. And at the end, we didn't have any constraint violations. And my third example is going to be on the use of ensemble of surrogate models. Because in the case of, complex engineering problems, we have more than one responses. For instance, if you consider a crashworthiness problem, you have cost, intrusion distance, acceleration, load. Different type of surrogate models can be find best for different responses. For instance, when we analyze such a problem, we find out that polynomial response surface was the best for predicting the mass. On the other hand, radial basis functions was the best for floor panel displacement in the case of full frontal impact, and support vector regression model was the most accurate for the floor panel displacement at the offset frontal impact condition. That is, as the new information comes, efficiency of surrogate model might also change, and then the use of a single surrogate model is risky. This is the main motivation. Then we have this simple weighted average model that I mentioned earlier. We assign weights to different surrogate model predictions, and selection of these weight factors are obtained through this optimization problem. Here we are designing the side rails in an automobile. Over here we have bumpers. Behind them we have those side rails. They absorb the kinetic energy in case of a crash. In order to reflect different design options, we used 4 design variables here. And in this problem, we also had some uncertain parameters like stress strain parameter, speed, offset distance, and occupant mass. Overall, we had 5 design variables and 4 random variables. That is, overall we had 9 variables in order to, we have 9 variables to relate to the desired response. We used 5 different surrogate models, including polynomial response surface, radial basis function, kriging, Gaussian process, and support vector regression. Now I am concentrating on the acceleration in the driver's seat for this response value in the crash problem. While generating the surrogate model, we used 100 training points, and at the end we found out that radial basis function was the most accurate surrogate model. Gaussian process model was the second best, and polynomial response was the third best model. And we also used different ensemble models, like ensemble based on simple averaging, parametric ensemble based on Goel, and ensemble based on Acar and Rais-Rouhani. We found out that this ensemble, the third ensemble, was giving more accurate surrogate model predictions compared to radial basis functions. The error is reduced by 13%, as we can see. In conclusion, what I did in this presentation was I started with motivating you for the use of surrogate models in a design optimization problem. And I introduced you different surrogate model types, and I discussed construction procedures for surrogate models. Do we have a question?
Is there a question? No, I think it was just some noise in the background.
Some noise, okay.
Yeah, okay. Sorry.
So I was concluding my talk. What I did was I motivated you for the use of surrogate models in your work. It can be either optimization or design space exploration or reliability computation, you name it. And I introduced you different surrogate model types, including polynomial response surface, kriging, support vector regression, and radial basis functions. And the concept of ensemble of surrogate models was presented in order to increase the robustness and accuracy of the surrogate model predictions. And I discussed three application problems with promising results. The first one was control arm design in an automobile. Second was optimization of a blade disc forgery joint. And the third example problem was an automobile crash problem. And we find out that the use of surrogate models resulted with good optimization results. I am active in this area in 2007. I developed a new method for ensemble of surrogate models with optimized weight factors. I also investigated various approaches for constructing ensemble of metamodels using local measures. I proposed a new method for optimizing the shape parameters of radial basis functions, and I also showed that using multiple surrogates is advantageous since the globally most accurate surrogate model does not necessarily lead to the optimum design. And I believe that collaborative work is important. I like to work with colleagues. We can co-supervise undergraduate students or graduate students. We can write joint papers, perform collaborative research. And I publish joint papers with researchers in other countries like India, with Palani Ramu, Korea, with Ixin Lee, and I have also collaborators in United States, and I am looking for new collaborations. If you would like to collaborate with me, you can contact me with my email, erdem.acar@gmail.com, and my webpage is located at this address that I show over here. With this, I conclude my talk. I thank you very much for inviting me for this special session. I would like to answer any question of yours.
The floor is now open for questions. You can either ask directly or you can also type in the chat. So to get the ball rolling, I have a question. So I have used surrogate-based optimization for some work many years ago. In your studies, have you found any relation between, like when you start off the optimization process, how do you decide on how many points you want to start with? Like, do you have an estimate saying, okay, I might need 100 points for this, or it's
Yes.
300? How do you work?
It depends. Yeah, it depends on what surrogate model I am going to use. If I am going to use a polynomial response surface, I generate 1.5 or 2 times the number of coefficients in the polynomial.
Okay.
I am using other surrogate models like kriging, radial basis functions, or neural networks, and I use 10 times the number of variables.
10 times. Wow. Okay.
10 times. Yeah.
And this is
That's
based on purely the number of the fitting, how the fitting works internally, or is it based on your experience with this type of?
Yeah, my experience and also experience of other researchers. There is a paper by D.R. Jones. He recommended using 10 times the number of variables. And it has been used with many researchers and find out a good start. And then actually you can improve the accuracy of your surrogate model with some adaptive sampling techniques. That is, you start with an LHS design, 10 times the number of variables, and then you construct your surrogate model. And then adaptively, you can add more points near the locations that you want to improve the accuracy of the model.
So So I have used Surrogate with LHS and Ego
Ego,
to
yeah.
with Ego. And
Uh-huh.
one of the difficulties is that it's, or at least I found it very difficult to, and this was many years ago, like I said,
Okay. Uh-huh.
I found it difficult to estimate the cost. With most local gradient based methods, you have an
Uh-huh.
estimate of the cost, or at least typically how many steps you might need. Now, it won't guarantee
Yeah.
global optimum that way, but and it's actually the kind of metrics that you showed actually makes sense, because you would need that many to precisely fit, avoid overfitting basically.
Mm-hmm.
So yeah, with Ego also I had to avoid overfitting, and
That's true.
ego would take me to the boundaries because that's where the accuracy was lowest.
Uh-huh.
So anyway, I was curious to know what your experience was. That's why I asked the question.
Yeah, ego is useful. Another way is to you search around the prediction variance, for instance. This is another way. Higher the prediction variance, where you want to put more points, for instance. It is uh, another way that you can approach the problem. That is, you want to reduce the variance in your prediction. So what you can do is, if you use kriging, it gives you prediction plus variance, and then
Correct.
you can put more points near where the variance is maximum.
Variance
This is
is high,
another
yes.
approach. Uh-huh.
Right.
Yeah.
Yeah, I found it to be a very powerful technique. It's applicable in many scenarios.
Uh-huh. That's true.
Yeah, and how do you like? Do you have your own codes, or do you use the Days toolbox? That is, I use the Days toolbox.
Yeah. For kriging, I use this. Yeah.
Okay. So actually, we just got a question on this. Let us know
Okay.
of any advanced software tools. So the I'll just type it out here. It's called Days Toolbox. It has been freely available for many years. I don't know. I
Yeah.
haven't checked in the recent past. So I put it in the chat window for
Uh-huh.
everyone.
Indeed. It is, I think, written by Lopaven, right?
Yeah,
Lopaven,
it's
2002.
yeah, it's in MATLAB, and it is
Sure.
freely available. I don't know if any
It
other,
is, yeah.
now that Python is the most popular language nowadays. Not sure if Days has a Python equivalent, but it is worth checking in case that you can.
Yeah, I am not sure. I have been using MATLAB. Yeah. I have, code for radial basis functions. And, MATLAB has its neural network toolbox. It is useful. And the support vector regression toolbox, it is useful. Yeah, MATLAB has all these. If you are using Octave, then you can find these functions too, I think.
Yeah, in Octave,
Uh-huh.
but the Days toolbox, does it work in Octave?
I am not sure. Since I have the license of MATLAB, I didn't use Octave,
Okay,
but
that is also worth checking. So
they were checking. Also, R might include, R. It might include
okay,
support vector regression or other surrogate models. Usually, I am happy with MATLAB. So, since it has this optimization capability, random variable
right.
modeling capability. So yeah, I didn't use Python or other language.
Yeah, I also use the MATLAB toolbox for Days.
Uh-huh.
I don't know if they have. So if there are, then it's worth. It's good. Any other questions or comments? The audience is more than welcome to join in. Sorry, were you saying something? I can't hear you. Looks like somebody's speaking in the background. So one of the last comment I have is one of the things I found is the MATLAB toolbox. maxes out on memory the larger, like I worked with large matrices as inputs and outputs.
Mhm.
When I was trying it out for CFD data, for example, I had to reduce the size of the data I was fitting. Otherwise, at some point the optimization would stop, the internal optimization of finding the two
True.
coefficients.
Yeah, yeah. Yeah,
Excellent.
in those cases, I think it is a good idea to perform a global sensitivity analysis using maybe SOBOL indices, and then eliminate the least important variables, and then using the important variables, you can construct sufficiently accurate surrogate models, I think.
Actually, that's what I like about the whole surrogate-based process. It gives you more information than just a model. It gives you
That's true.
information about correlations in the parameters and the type of
Yes.
fit. The error can be
Yes.
used in driving an optimization search. So
Yes.
that's one of the nice things about surrogate-based optimization process.
Sure,
And
sure.
there is enough flexibility there, I think. So
That's true. It's flexibility is a good property of surrogate models. Yes.
it looks like we don't have any more questions. So thank you, Professor Raja, very much for participating.
Thank you for inviting me. Thank you very much.
Now, is it okay if the audience has questions after your talk and they get in touch with you through email?
Sure, sure. Just send me an email. Sure.
Okay.
You can contact me with this email that is shown in the screen anytime.
Okay, excellent. Thank you so much.
Thank you very much. Have a nice evening.
I think it's evening for you, right? So have a good evening.
You too.
Yeah.
You too.
Yeah. Okay.
Thank you.
Bye.
Thank you. Thank you.
Bye.